Welcome back to lesson 14 of our discussion of the transport layer. In our last lesson, we were discussing flow control. Now we're going to move on to another very similar issue, congestion control. So let's get started. In the previous sections, we examined both the general principles and specific TCP mechanisms used to provide for reliable data transfer service in the face of packet loss. Such loss typically results from overflow in the router buffers as the network becomes congested. Packet retransmission thus treats a symptom of a network congestion, the loss of a specific transport layer segment, but does not treat the cause of the network congestion, too many sources attempting to send data at too high a rate. To treat the cause of network congestion, mechanisms are needed to throttle senders in the face of network congestions. In this section, we consider the problem of congestion control in a general context, seeking to understand why congestion is a bad thing, how congestion is manifested in the performance received by upper layer applications, and various approaches that can be taken to avoid or react to network congestion. Let's begin our general study of congestion control by examining three increasingly complex scenarios in which congestion occurs. In each case, we'll look at why congestion occurs in the first place and at the cost of congestion in terms of resources not fully utilized and poor performance received by the end systems. Scenario 1. We begin by considering perhaps the simplest congestion scenario possible. Two hosts, A and B, each with a connection that shares a single hop between source and destination, as shown in this figure on your screen. Let's assume that the application in host A is sending data into the connection at an average rate of AN, for application N. The rate at which the transport layer sends segments containing original data and retransmitted data into the network will be denoted as TN, transport layer N, and we'll measure this in bytes per second. Remember, the application is sending data to the lower layer, transport, for service. That would be the AN. Then the transport layer, after adding its own header, sends data into the next layer for service. That's the TN. TN is sometimes referred to as the offered load to the network. The underlying transport level protocol is a simple one. Data is encapsulated and sent, no error recovery, no flow control, or congestion control is performed. Ignoring the additional overhead due to the adding transport and lower layer header information, the rate at which host A offers traffic to the router is not exceptional. Host B operates in a similar manner, and we assume for simplicity that it too is sending at the same rate, AN and TN. Packets from host A and B pass through a router and over a shared outgoing link of capacity we'll call R. The router has buffers that allows it to store incoming packets when the packet arrival rate exceeds the outgoing link's capacity. In this first scenario, we assume that the router has an infinite amount of buffer space. This figure on your screen plots a sample performance of host A's connection under this first scenario. The left graph plots the per connection throughput as a function of the connection sending rate for sending rate between 0 and R divided by 2. The throughput of the receiver equals the sender's rate. Everything sent by the sender is received at the receiver with a finite delay. When the sending rate is above R divided by 2, however, the throughput is still only R divided by 2. This upper level on throughput is a consequence of sharing the link capacity between two connections. As we discussed earlier, a TCP connection is full duplex, so no matter how high hosts A and B set their sending rates, they will never see a throughput higher than capacity divided by 2, or R divided by 2. Achieving a per connection throughput of capacity divided by 2 might actually appear to be a good thing, because the link is fully utilized in delivering packets to their destinations. The right-hand graph of this figure, however, shows the consequence of operating near link capacity. As the sending rate approaches capacity divided by 2 from the left, the average delay becomes larger and larger. When the sending rate exceeds capacity divided by 2, the average number of queued packets in the router is unbounded, and the average delay between the source and the destination becomes infinite, assuming that the connections operate at these sending rates for an infinite period of time, and there is an infinite amount of buffer space available. Recall that we said in this example that the router has an infinite buffer. Therefore, while operating at an aggregate throughput of near capacity may be ideal from a throughput standpoint, it is far from ideal from a delay standpoint. Even in this idealized scenario, we've already found one cost of a congested network. Large queuing delays are experienced as the packet arrival rate nears the link capacity. Now let's slightly modify scenario 1 in the following 2 ways. First, the amount of router buffering is assumed to be finite. What this means is that packets will be dropped when arriving to an already full buffer. Second, we assume that each connection is reliable. That is, if a packet containing a transport level segment is dropped at the router, the sender will eventually retransmit it. Because packets can be retransmitted, we must now be more careful with our use of the term sending rate. The performance realized under scenario 2 will now depend strongly on how retransmission is performed. First, consider the unrealistic case that host A can somehow determine whether or not a buffer is free in the router, and thus sends a packet only when a buffer is free, in which case no loss would occur. Watch as our packet travels the network. Now you notice that it found that the buffer had free space, and therefore it was transmitted on up to the receiving unit. Consider the slightly more realistic case that the sender retransmits only when a packet is known for certain to be lost. Watch this communication. Sending the unit, sends it out, puts it on the network, reaches the destination, there's no buffer space, and it's lost. A timeout occurs, let's say. The sending unit knows that the packet has been lost. It sends it again. This time there is free buffer space, and it is passed on up to the receiving unit. It is possible that the sending host might set its timeout large enough to be virtually assured that a packet that has not been acknowledged has been lost. We see here another cost of a congested network. The sender must perform retransmissions in order to compensate for dropped or lost packets due to the buffer overflow. Finally, let's consider the case that the sender may time out prematurely and retransmit a packet that has been delayed in the queue but not yet lost. Watch this transmission. Packets queued up, sent to the transport layer, passed to the network, buffer's free, passes it in, the timeout was set too short, it sends another one, and now we have duplicate packets. Both have been received at the receiving unit. In this case, both the original data packet and the retransmission may reach the receiver. Of course, the receiver only needs one copy of this packet and will discard the retransmission. In this case, the work done by the router in forwarding the retransmitted copy of the original packet was wasted, as the receiver will have already received the original copy of this packet. The router would have better used the link transmission capacity to send a different packet instead. Here then is yet another cost of a congested network. Unneeded retransmissions by the sender in the face of large delays may cause a router to use its link bandwidth to forward unneeded copies of a packet. Well, before we go to our third scenario, why don't we take a break and review our notes about this one? And whenever you're ready, come on back and we'll do it again.